We started this on Monday. The problem is here drawn in this diagram, a cart on a ramp. The cart has a mass of 0.223 kilograms. The ramp is at an angle of 26.8 degrees. Over to the left here is the analysis. Here is the forces acting on the cart, which is our object. This would be the normal force, and then here that's the gravitational force, and we calculated that knowing the mass and the gravitational field strength, right? That is the mass times g, 9.8. That's equal to the gravitational force. So in this case, 0.22, actually I think we used 0 kilograms yesterday, times 9.8 newtons per every 1 kilogram results in that gravitational force. So if I take this trigonometry here, this geometry, and I redraw it over here, I see that I have an angle and a side of this right triangle, so that means I can calculate anything else. I see this angle, and then the opposite side is that, so I know that the sine of 26.8 degrees equals the x component of the gravitational force divided by the hypotenuse, 2.16 newtons, and cosine of 26.8 degrees is going to equal the y component of the gravitational force divided by the hypotenuse in this case. And here are the calculations for the x and y components of the gravitational force. 0.97 newtons is the x component, 1.93 newtons is the y component. So what are these? Let's look back over here at our diagram. The y component is right here, and based on this diagram, it's apparent that, remember, this is the cart, and this x-axis would represent the ramp, and the cart is not accelerating down into the ramp or up off the ramp, so this component must be equal to the normal force. So 1.93 newtons is the normal force. So we've calculated the normal force in this case. It is less than the gravitational force, and it would make sense that as the ramp increases its angle, the normal force would decrease. Now, the x component, what is that? That is this, I'm going to do red here, this component right here, and that's parallel to the x-axis. In fact, this is not canceled out by anything, so it's the only vector left, the only force vector left, and this is the net force in this situation. If we go up here to our original situation, we have this first vector, and we add to it this second vector here, head to tail. That's the result of those two, and it's the force that's making the cart go down the ramp. It's a gravitational force, but it's only a component of it. It's only some fraction of the original gravitational force. So Newton's second law, acceleration equals net force over mass. The net force for this particular case is that x component of the gravitational force, 0.97 newtons. The mass, 0.223 kg is the actual mass that I measured. That equals 4.35, and the units would be acceleration units, meters per second squared. So that's the acceleration of the cart down the ramp. In class, we actually calculated the velocity as it rolled down the ramp, and we came pretty close. This is a kinematic equation you might remember. So we're able to link, now knowing acceleration, we're able to now take acceleration, put it in a kinematics equation, and link our force analysis to motion. And this came out to be, I put in for delta x, we had to go 0.9 meters down the ramp, and I think it came out to be about 2.8 meters per second when delta x is equal to 0.9 meters. And we put this in right there, and it came out pretty close. We made some measurements of the cart going down the ramp, and the acceleration was right on, and this was very close. It works.